Hey Radical Scientists, so here it is, probably one of the most requested videos, walkthroughs through our class together. I'm looking at specifically week 1's level 3 assignment titled on electromagnetic waves, and even more particularly at the part 2, the electromagnetic spectrum. A quick intro to what this part is all about. We've looked at the electromagnetic spectrum and we can understand them as waves, right? But really what I'm trying to get us to really understand here is one, the relationship between wavelength and frequency that generate all different types of waves, electromagnetic waves, infrared, gamma rays, X-rays, visible light, all of these waves traveling at the speed of light, which we represent through the value c. And on the other hand, it's also understanding outside of this mathematical relationship, it's understanding that these waves, right, these oscillations of charge between positive and negative are happening in these distance frames within a space, and as well as how often they're happening within that specific point in our universe. That starts getting more conceptual again outside of my own boundaries, but my hope is just to give you a little more practice again to some of the mathematical practices that we're going to develop with some maybe at first scary numbers, right? They look all over the place, but I assure you after completing all of this part 2, you will feel much more better about dividing, solving for an unknown variable. So with that, folks, here it is. Let's just take a look at some examples for part 2. All right, folks, so let's take a look at this table here, which is at the core, the center of this part 2, right? Where we're looking at different types of radiation, again, electromagnetic radiation, of different names that we've chosen to just classify different types of waves that all fall within a spectrum, right? Meaning that we have different types of waves all traveling at the same speed, right? But that they have different lengths, right? And each time the length is affected equally, the frequency is going to be changed. So you can even understand these waves in one of these two, because honestly, once we know the frequency, we can solve for the wave. Once we know the wave, we can solve for the frequency of any different type of electromagnetic radiation. Pulling all of this conceptual stuff to the side though, at the end of the day, this is what we're trying to do, solving for this relationship, right? Which is once again explained by this equation up here. The speed of the wave, which is constant for speed of light, is always equal no matter what type of wave, by the wavelength and the frequency. How long that wave is, how long it goes from like peak to peak, if we have something like this, right? From peak to peak. And because this is just a length, right, it doesn't show us how fast it's going, also how often this wave is happening. So this wave can look like this but happen super slowly, right, meaning that there would be a longer frequency, or it can happen really short, and you can imagine this wave is moving incredibly fast despite it being that long. That's at the end of the day what we're trying to solve for, one or the other. And in this case, we know what the frequency is. We know how often, for example, if it's happening super long or it's happening super fast. With this information in mind, let's do two things. One, recognize that what we're looking for is in this middle column, the wavelength range. So we have to use what we are already provided with to solve for that wavelength, right? This equation tells us that we can relate the speed of a wave with its wavelength and frequency. We need to solve for the wavelength, but we already know what the frequency is. It's provided down here, and we also know what the speed of wave is for all lights. C is equal to the speed of light, 2.998 meters times 10 to the 8 meters per second. I'm gonna go ahead and just write this over here for our first known quantity, the speed of light, which we will replace for c, equals the wavelength that we're looking for. I'm gonna go ahead and write that in green. Also no frequency, right? We see this number on our right side of this little chart here, which let's look at infrared waves for now. This is just a general outline, and we're going to focus on one of these values, right? One end of this frequency range, right? From here to here, these are two different frequencies, and infrareds fall anywhere in between these. Let's focus on the first one, which is 10 to the 13 hertz, right? I'm gonna go ahead and do a couple of things here. One, I'm gonna write a 1 times 10 to the 13th. Numerically, we know that this 1 times 10 to the 13th and 10 to the 13th are the same. Anything multiplied by 1 is itself. Anything divided by 1 is itself. We can just go ahead and add in 1 here. We'll see how that's helpful in a quick moment. And I'm gonna go ahead and rewrite the hertz, right? This Hz unit, which can also be expressed in s to the negative 1, as also 1 to the s. These are all the same thing. They're the same unit in different letters, configurations. And once again, you'll see why this is a little more useful to think about in frequency in just a quick moment right here. I'm gonna go ahead and draw this in the meantime. Okay, now we have two known values solving for a third. And once again, the focus really is on this green wavelength that we do not know. So we're gonna go ahead and just try to isolate it, right? Focus on it exclusively so we can just work around with what we have around it. So I'm gonna go ahead and divide both sides by this 1 to the 10th to the 13th 1/2 times 1, sorry. And over here, 1 times 10 to the 13th 1/2. Anything over itself, no matter how scary and complicated it looks like, will always equal 1, right? So that cancels out. And over here on the left, we have a bit of more complicated situation here. So we're gonna go ahead and piece it piece by piece so that we understand how we will simplify this to a simpler number and ultimately an answer. Let's look at the numbers first, right? We see a 2.998 divided by a 1, which would equal, as we mentioned earlier, right, 2.998 simply. Takes care of one of these numbers, right? Let's focus on the next, which are the tens. A couple ways to do this. You can definitely use your calculator, but in this case, I'm gonna use a neat trick in which when we have exponents of a common base, what I mean by that is that both these have a 10 to the something, right? 10 to the 8th, 10 to the 13th, but they're ultimately 10. Common bases of exponents, we're gonna go ahead and, because they're being divided this way, subtract them. There's a long way to kind of approach this. 10 times 10, 10 times 10, 10, you do that 8 times, 10 times 10, 10, 10, do that 13 times. You'll see that 8 of those will cancel out and you'll be left with 5 of them underneath, and you can see that that matches up with 8 minus 13, which should equal us negative 5 over here, right? Because they're in the bottom. And we drop this over here to be 10 to the negative 5. Now, here is where the 1 over s takes place, right? 1 over s, which again is a unit of frequency, hertz, seconds to the negative 1. The reason why it is this way is because, well, a way that it helps us is that if we look at over here, we have two different units. We have the speed unit and then we have a frequency unit, which look very distinct. But if you recognize that, basically what we're having to do here is divide 1 meters over second, 1 over second. A couple things can happen. We can rewrite this as a different multiplication of the, what is it called? Not the inverse. I forget honestly what this is like. I will edit this as I record it, but you can notice that we can flip this around and we can now multiply it as opposed to divide. And here, really clearly, we see that these s's cancel out, one on top of the other. Another way to think about this is just recognizing that in both of these cases, these s's are the denominator. They both happen to be in the same place and they're one on top of each other. Anything over itself is 1. So you can think about it in either of these ways, right? The s's will cancel out, leaving us with just an m at the top, which is what we're looking for. We're looking for a type of distance, a wavelength distance in meters. We're left with just the meters once all of these things cancel out with a number. This ultimately equals our frequency, and lo and behold, we have one of the numbers for this frequency range for letter C of this, right? The next step, which I won't do, but I will encourage you to do so, is to now look into the second range of that frequency, right? We have one endpoint of a spectrum. We need the other endpoint of that spectrum, right? We're going to keep doing this as we continue to solve for the different problems. Hope that helps, and thank you so much everyone for your work.